Good morning and good afternoon, everyone. Welcome to our third edition of Next Frontier, Future of Elderly Care, Robotics for Healthy Aging. My name is Li Binggu. I'm the head of academic relations at SwissNext in China, the science consulate of Switzerland in China. We are here to show the best of Switzerland, build bridges, and connect with China in education, research, and innovation. Next Frontier is our latest webinar series, which spotlights cutting-edge research in Switzerland and China with a focus on Swiss National Centers of Competence in Research, so the NCCRs, and Chinese top-class research institutions. The aim is to spark potential exchanges and future collaborations. Today, we will learn about emerging robotics technologies and products that are customized for the elderly. We are very honored to have invited prominent speakers from the Swiss National Center of Competence in Research, NCCR Robotics, EPFL, ETH Zurich, and Shanghai Jiao Tong University. Before we start, I'd like to kindly remind our audience that at the bottom of the Zoom interface, you can find the Q&A function. So please type in your questions during the webinar, and we will answer them in the Q&A session. Without further ado, I'd like to introduce our first speaker, Professor Pierre Dillenburg, Associate Vice President for Education at EPFL, Core PI at NCCR Robotics. Professor Dillenburg started his research on learning technologies in 1984. In 1986, he has been one of the first in the world to apply machine learning to develop a self-improving teaching system. He obtained his PhD in computer science from the University of Lancaster. He joined EPFL in 2002 and is currently full professor in learning technologies in the School of Computer and Communication Sciences, where he is also the head of the lab Computer-Human Interaction for Learning and Instruction. Professor Dillenburg, the floor is yours.
Thank you very much. Let me share my screen. Can you stop sharing your screens? Yeah. Can you see my screen? Good. So as it was just said, I'm not an expert in healthy aging. All my research has been in my life on younger learners, on school or secondary school children, on learning technologies. And we developed this, but then we realized there is a potential. We developed this small robot that has two main features, that fits in a hand, and it has two main features. The first feature is that it provides user with haptic feedback. You feel the forces in your hand when you do any kind of game or learning activity or healthy aging activity. The second feature is that it's located itself on a paper sheet as big as Switzerland, if we want, by 1/4 millimeter. So because it uses a dot pattern. So this was designed for schools, not for healthy aging. I will come to healthy aging in a minute. So what are the two elements on this robot? So we have a patented mechanism that provides the haptic feedback, and if the robot goes in one direction and the user pulls it in the other direction, it does not break the engine of the robot. The second feature is that the LEDs and cameras that look at the paper, and we use the Anoto pattern, as I mentioned, to locate extremely accurately at any time the robot on the paper, which means that when we change the paper sheets, we change the learning activity. The metaphor was a pen. You use the same pen to do a lot of learning activities on different pieces of paper. The same here, the same robot can be used on a variety of sheets of paper if each of them implement a different activity or game. So this is a more funny one when you don't interact with one robot, but you interact with a group of robots. And again, we designed some activities for schools up to a moment where a colleague from rehabilitation in the NCCR said, Pierre, I have some ideas about your robot. Maybe you could use them for stroke rehabilitation. And he told me that stroke patients have to do not so fun rehabilitation activities, like cleaning a clean table, which is not extremely motivated. It's at the point that only 30% of the stroke patients actually do the rehabilitation. So For that, we designed, he asked us, can you gamify rehabilitation? So this is a stroke patient, is playing Pac-Man. So there are two ghosts, we try to catch him, and he tries to catch the fruits. And you will see the speed and the number of ghosts can be tuned, the complexity of the maze as well. Of course, when he is caught by the ghost, he does not die, but he loses fruits and has to start again. We can also make it more difficult, like rotating on the top of a fruit to get the fruit, but even like that, it's maybe quite challenging depending on the stroke patient we are considering. So we tried that, we tested this activity also with children with problems, a lot of children with neurological disease. But we conducted experiment where the stroke patient had to play with two versions of the game. One gamified, one non-gamified. The gamification was the fact that two ghosts tried to catch you. The non-gamified was the same kind of movement on the same map, but without the gamification of the ghosts. And as you can see on the left, the standard performance, and you see how we computed the standard performance on the bottom, was significantly higher with gamification. There were some trade-off, like if you increase speed, you lose accuracy. We, of course, took these things into consideration. When we look a bit closer at the people, you see that we had two kinds of stroke. Well, we clustered our users into two categories: those with moderate, with less impaired, lower consequence from the stroke, and higher consequence of the stroke in blue. And you see on the left column that there is an interaction effect, that those who are not too affected by the stroke actually benefit even more of the activity. And this and discussion with potential investors led us to the idea that we might look not at stroke market, the stroke rehabilitation market, but the healthy aging market. And we did experiment where we tried our game with people between 60 and 80 in yellow, and EPFL students, so between 20 and 30 in blue. And you see that the young people benefit more than the older elderly one, but still there is an interesting improvement for elderly persons. So that is paving the road of this project that we call Silver Haptic. Can we develop a variety of games? Pac-Man is just an example, a variety of games for elderly people at home or in elderly centers in the community or elderly houses to practice motor, cognitive, and social function. You will ask me, which social function? Let me explain in a second. So before that, something extremely important is that these games can be tailored, they can be adapted to the performance of the user. The number of ghosts, 0, 1, 2, the speed of ghosts, the complexity of the maze, the distance of the maze, how big is the maze, it has an effect on the mobility of the player. The game strategy, whether we help haptically, we help them with the haptic feedback to drive right, or we disturb them to see how quickly they react. Whether, for instance, in the Pac-Man game, they had a penalty if they kidnapped the robot or they cross the wall. So these large paper sheets are low cost and easy to print, but we went one step further and we printed the same dot pattern on these tiles. These tiles are attached to each other with a small magnet. And you can actually not only play the game, but design the game by assembling the tiles. Here there are two people who are playing together. I mentioned the social function. They have to be on the same color to be able to connect something, but they are still chased by the robot. And you see they have designed themselves the space where they're playing. Here they played in a collaborative mode, but we also tried it with playing in competitive mode. That's a very cool thing. We can play with the two functions. And the competitive was kind of more fun for high performance, but less fun for low performing people. So now we recently did something even more interesting, is that on the left, you are someone playing with a real robot, and on the right there is somebody fighting with the one on the left, but fighting online. The idea is that you can practice social skills, social interaction. We know how important are social interaction in healthy aging. You can practice in side by side, which is great. But if your grandson is in Canada or wherever far away from you, you can also play with your grandson online, and you can feel, the elderly person can feel in his hand, in some way, the hand of the grandson. He can feel in his hand the force of the other player online. This can be done playing with another player. Oh, more interestingly, or even interestingly, it can be done by playing with a therapist. The therapist can not spend a lot of time with every patient, every person, but in case of therapy, or in case of there is a manager or some kind of assistance in the elderly house, this person can also play when the elderly people is on site, but you can continue to play with when the person is back home. So that's the basic idea, is that we extend activities from place where there is support to the home activities, and we can still keep support. So the basic value of this robot is not the robot itself. Let's be honest, is the quality of the game that will be designed with the robot. But the robot and this, with paper sheet or with haptic tiles, this robot provides the opportunity to create real nice games that push the elderly people to practice 3 key cognitive functions: motor functions, cognitive function. There is a lot of strategy. If you play Pac-Man, like you go in a corner to attract the robot, and then you cross quickly the map. So cognitive skills, motor skills, and social interaction in presence or at distance, and at distance with a friend, a grandson, or a professional. That's the strength of the robot. The second thing is that it provides feedback to the platform in real time. So we can do a very close follow-up of the people playing the game to observe, for instance, how much they progress or how much they do not regress. And also you can use this real-time data collection to make the game adaptive. If they fail too often, then you make the things a bit easier. And finally, the idea beyond this robot was to have a low-cost platform. It's not a toy. It's not something that can be produced for $10. It's slightly more expensive. We're redesigning the tool, the hardware, to make it easier to produce, but it's not the same range of cost as some of the medical technologies. So it's kind of a medium price, more the price of a game, probably not the price of a toy, but that's something that can be afforded for home activities. That's it for me. Thank you very much for your attention.
Thank you, Professor Dillenburg, for the interesting talk. Well, due to other commitments, Professor Dillenburg have to leave us now. And if you have any question for him, please leave them in the Q&A box, and we will forward them to him and provide you with his answers by email. Thank you once again, Professor Dillenburg, for your presentation. Now I'm delighted to introduce our second speaker, Professor Guangzhong Yang, Chair Professor and Founding Dean of the Institute of Medical Robotics, Shanghai Jiao Tong University. He was the founder and director of the Hamlin Center for Robotic Surgery, Imperial College London. Professor Yang's main research interests include medical imaging, sensing, and robotics. He is editor-in-chief of Science Robotics, a journal of the science family dedicated to the latest advances in robotics and how it enables or underpins new scientific discoveries. Professor Yang, the floor is yours.
Thank you very much indeed for inviting me to give this talk. So it follows on from the first speaker very well, that what I'm going to talk about is really about elderly care. Why do we need robotics for healthy aging? So as you know, that the global health, the general trend is that aging population, rising cost, and also prevention, urbanization, all these issues are driving towards that, in terms of healthcare, we really need to look at personalized medicine and also that managing the chronic and infectious diseases. So under such a general trend that there are many issues, particularly for aging. Let me just highlight a few diseases, for instance, dementia, that it's a progressive degenerative brain syndrome that affects memory, thinking, behavior, and emotion. And the care for the aging dementia causing a lot of trouble, that both for the patient himself or herself, as well as the family. And the cardiovascular diseases that account for 30% of deaths worldwide, and disability. So all these problems are major factors for our aging society. And so currently, when you look at the burden of chronic diseases, including diabetics, hypertension, and chronic heart failure, asthma, depression, and so on, and this are all causing a tremendous burden economically. And we're really looking at the 5% of the population using over 60% of the healthcare costs. So when we look at the aging body, that what are the things that we need assistance for? That clearly brain and nervous system, that you need robotics for assistance, and for respiratory system, that for instance COPD and all these issues that require assistance, and musculoskeletal systems. This is perhaps one of the area in terms of rehabilitation robots have its biggest impact. And of course that, in terms of visual and sensory systems, and all these are problems that you have to deal with. So talk about the robotics and all the others. What are the technologies that we need to develop? Not only, limited to robotics. So first, that when we look at this, is really need to closing this loop, what we call the prevention, diagnosis, treatment, and evaluation. Prevention, clearly that the need for imaging, diagnosis, for sensing, and treatment, you need to have minimally invasive techniques. For surgery, for instance, surgical robots, and evaluation, that includes that rehabilitation devices, that such as those that I mentioned in the first speaker, and also those devices that can be worn, wearable devices, and also implantable devices as well. So the first, that in imaging, there are tremendous advances that allow us to diagnose disease early, and also that the use of sensing technologies, both wearable and implantable, these make significant inroads into the diagnosis and also evaluation as well as prevention. But for wearable devices, implantable devices, and these are widely used in clinical care for the aged group. That, the reason for that is that, as I mentioned, as you have an aging body, that to enhance the sensory feedback, to enhance the motor function, and also to enhance the independence, and all these are important. But coming to the focus of my talk today is about the robotics. So in terms of robotics, one of the areas that there has been tremendous amount of research being dedicated to is in robotic surgery. And these are very much related to the aging society. The reason for that is that for octogenarians, and there's very, the trauma one can experience due to surgery is very much limited. So by using minimally invasive means, that it will allow us to perform surgery, otherwise it will be too challenging or too risky for this age group. So laparoscopic surgery, orthopedic surgery, endoluminal surgery, and neurosurgery, and there have been many platforms that have been developed. But let me just focus on one area, for instance, that for orthopedic surgery, for the aging group, one of the biggest problem that one has to deal with is really that for the musculoskeletal system, how do you deal with joint replacement, for instance? So the use of robotic systems which will give us the accuracy and also that consistency for the procedure. So this is one of the platform that we are involved in developing, and as you can see here, that the robot is very easy to use and can be integrated with surgical workflow very well. And the most significant part is that it reduces the complication and also increase the consistency, accuracy, and also all these areas. So those type of technologies are getting more and more used in robotic surgery, and also that in the particularly for the age group. But there are more techniques that are currently being developed in different institutions as well as in commercial organizations. For instance, that as shown here, that in terms of exoskeletons, that for the both for the upper and the lower exoskeletons for enhancing the musculoskeletal functions. And I think that those type of systems that you will see more. But in terms of technological trend, and more devices are moving towards what we call soft exoskeleton systems. That, for instance, for the Harvard group, that they have developed several generations of soft exoskeletons can be used. Another area that has enjoyed a lot of development is really that in the human-robot interaction, whether this is using EMG, EEG, FNIRS, and this allows what we call a more active assistance that can be used in practice. Commercially, that there are many platforms being used that already on the market. The Armeo system for upper limb, the Exo Bionics that for exoskeletal systems, and the Gypsy, Locomat, and to name a few. And certainly that there are many systems developed by Swiss companies and also research groups. So what are the challenges and developments that also the routes that different groups being taken, that from rigid systems there are many different embodiments that here I listed a few, and also that the soft exoskeleton, as I mentioned earlier, are attracting a lot of interest, not only for its safety, ease to use, but also in terms of low cost. And other examples in terms of actuation, that this hybrid systems, soft and rigid, provide you with the rigidity and also strength that you are looking for. So a couple of years ago, that Robert Reiner and myself, along with Paulo Dario, that wrote this article for Science Robotics as an editorial, and to highlight the importance to integrate and to empower. So robots is not only just for providing physical support, but it's also important to integrate this into the system, that therefore it provides seamless integration between the human and the robot. From that perspective, there are many new developments that have been reported in Science Robotics, for which I'm the founding editor. For instance, that this is one example that by Professor Clark and his group on biomimetic sensory feedback through peripheral nerve stimulation. And the idea here is to improve dexterous use of bionic hand. As we know that the mechanical grasping and all the things in terms of bionic hand currently, they can be done, but more that we want to add back the sensory feedback. And this allows us to manipulate much more complex objects, soft objects, and also delicate objects that for functions that that needs to be restored. So this is the general direction that the research community is driving towards, and partially due to the advances in terms of material science, the sensor integration, as well as our ability in terms of modeling the world. And for this group, that for this paper, for instance, that they have demonstrated that for managing different objects, these are all daily objects that we found it taken for granted for manipulating, but for patients with prosthetics, and these are difficult for them to do. As you can see here, the improvements that with sensory feedback. And also another work that by Nitish Thakur from Johns Hopkins University, that the use of neuromorphic multilayer eDermis that to perceive touch and also pain. So here that this sensorized skin that allow you not only to have the sensory feedback, that to allow you to perceive touch and pain, but also that to increase the dexterity. What is also novel here is the introduction of the neuromorphic model. Therefore, that you have a very efficient computational framework that is akin to how human that the sensory system work. So with this, that you can, as you can see here, that from the EEG and so on, that the movement, you can have better perception of the objects in the world and also have the sensory feedback. In this case, to look at the reflex that due to pain. So to put this together, that I think the future development of robots for rehabilitation, for elderly care, for assistive devices, and so on, that will be this principle, what we call the 4 Cs. So it needs to be compliant and needs to be continuing, that rather than the more traditional robot devices, and also they need to be cooperative and also with cognitive power. So this brings us to the future consideration of robots, whether this being assistive or that for surgical robots, in fact, that is the different levels of automation. That for assistive devices, for wearable devices, obviously you want the human to be able to wear it without actually perceiving it is there. So it is seamless, working seamlessly in the background. So for surgical robots, that we are still working in this area, 0, 1, or 2, with for robot assistance or task autonomy. But for those assistive devices, certainly we want to push this to a higher level, and level 4 or maybe even level 5. And this the focus that we are all working on within the community. So just draw this to conclude that to conclusion. For the robotics for elderly care, there are many unsolved problems, but on the other hand, we are also making significant inroads into different platforms that can be used in practice. The use of soft robotics, soft exoskeletons, and all this are representing tangible directions for bringing those technologies into clinical practice and also into people's home. Other related areas that for our aging society are robots used for hospital automation, for surgery, and also in other areas. So these are the 3 areas that, in fact, the Robotics Institute in Shanghai Jiao Tong University, that for which I've established a couple of years ago, back in Shanghai, it is focusing on. So very much hope we'll have the opportunity to exchange ideas, and also for those of you who are interested in knowing a bit more about what we are doing, visit us in future. Thank you very much, and thank you yet again for inviting me to give this short presentation, give an overview of what we do, and also what the community is focusing on, and potential future directions the community is working towards. Thank you very much.
Thank you, Professor Yang, for the insightful presentation. We will have more interaction during the Q&A session with you. Now I'm glad to introduce our next speaker, Professor Robert Riener, full professor for sensory motor systems, Department of Health Sciences and Technology at ETH Zurich. He is also full professor of medicine, University Hospital, Biogrist at University of Zurich, and co-director of NCCR Robotics. His work focuses on the investigation of the sensory motor interactions between human and machine, and the development of user cooperative rehabilitation robots, exoskeletons, and virtual reality technologies. Professor Riener is the initiator and organizer of the Cyberslon, which was awarded with the European Excellence Award, the Yahoo Sports Technology Award, and with 2 categories of the Reimagine Education Award. Professor Riener, the floor is yours.
Thank you for the kind introduction and also invitation. So I hope I can show you how rehabilitation robots can support and cooperate and even motivate people with impairments. So I'm affiliated to ETH Zurich and the University Hospital, as you already said. Next slide, you see that we have a tremendous high number of patients suffering from stroke. Next. And in the world, it's about 60 million cases every year of new patients, and they unfortunately suffer from lesions, from hemiplegia in most cases, and that can be treated by training. Next slide. However, most of the time, these patients are lying in bed. So they are sleeping, they're eating, they are relaxing because they might be exhausted. And unfortunately, the time which could be used for therapy, for movement, is too limited. Although we know that a higher number of training, higher intensity of training leads to better outcome of these patients. Next slide. Therefore, we can improve, not as alternative, it's not an alternative to physical therapy, but an addition. It's a tool for therapists. There are machines for the lower extremities, different kind of end effector based and exoskeletal devices. And in the next slide, you see that we have a special machine like the Lokomat or upper extremity machines. Yeah, you can go on. For the upper extremity, we can also distinguish between exoskeletal devices and end effector based devices. You see already here the Armin or AmioPower, which has been presented by Professor Young already before. Next slide. The Armin, that's a device which has been developed in my lab already many years ago. We have many different generations of this device, and it is the first exoskeletal device which has been used and applied to the therapy of stroke patients. Next slide. Here you see an overview of all the generations of that device. We started already 2003. The first device, Armin 1, came out 2005 with only 4 degrees of freedom. We added 2 more degrees of freedom to also move the hand and the lower arm, additionally to the shoulder and elbow actuation. Armin 3 then has even a 7th degree of freedom to actuate also the hand of the patients. It has a special interactive control. Many different games have been implemented, and that version was used for clinical study. Then we made further versions with some more sensing to improve the quality assurance and rehabilitation evaluation. And we have a pediatric version, the Charmin, used for children. In the next click, you see that there's also a commercial version of the device available, which is being called AmioPower. Next. You see the main result of our clinical study, which we did some years ago. In the dark black line, you see the outcome of a robotic group. About 38 patients have been treated with the Armin device, and we had 35 controls, which have been treated with conventional therapy and physio and occupational therapy. And you see that the gray shaded area is the 8 weeks of the training. And you see already after 4 weeks, we get the same outcome in the robotic group as we get after 8 weeks only in the conventional group. And the differences were significant. However, they're still small, and you see that they seem to wash out in the later phase of the follow-up. If you click again, we see that there's a slope still. Probably if we would have done the therapy longer, 4 weeks longer, we could have seen a bigger increase, I assume. And what you also saw, not shown in this slide, is that the more severely affected patients, they have a much better improvement compared to the conventional group, and that stays over the follow-up phase. Next. So what we have to do to make the difference even better between the robotic group and the conventional group is to increase the intensity. Next. And we can increase it by engaging and motivating the patient, because then they do the training faster, they come to the sessions, we get a better patient compliance, and so on. Next. And for this, we did implement a path controller. Click twice. And then you see that we can control the arm of the patient in a way that there's more freedom to move inside a certain path. And this way, we can allow more deviations. We can still support the patients if they're weak, and implemented in many different kind of games, for example. Next. We did implement this, for example, in a game next with where you see here a special activity of daily life, brushing the teeth. And here we apply this path control, and we can make that path also more narrow if the patients need more guidance or not. So we can allow different kind and different levels of interactivity between the robot and the patient. Next. We implemented the same controller in the Lokomat for gait training, which was developed in Zurich before my time, that device. Here, the movement of the foot or the ankle joint actually also fulfills this or was guided by this path controller, where we can allow deviation from a fixed position and support as much as needed. Next. And then we have this motivational problem, because the training can be quite boring. And the patients do not show up anymore to the sessions. Oh, we should, because we should improve their gait functions. Next, and for this we have implemented also many different games. The idea is that not only physical activity, but next, if you also have cognitive activity, we can increase the neuroplastic effects in that kind of training. Next, we call this engagement. The engagement, if that is stronger, physical as well as a cognitive or mental engagement, we can get a stronger neuroplastic effect, meaning a better outcome, a better quality of life for the patients. Next. So in the Lokomat, we have implemented a game scenario where the people can walk through a virtual environment, and it's easy to instruct them because they immediately see and understand what they have to do. We can add some nice sunshine, we can add animals inside this path, we can add obstacles where the people know what they have to do. They have to lift the foot to go and walk over that obstacle, for example. So it's very intuitive and also very motivating. We can make it very exciting. We can add some ghosts or some kind of funny elements to enjoy the patients, and this way engage them and increase the outcome. Next. Game for soccer for children. Also very engaging for the children when they play the soccer game. Next, please. And also in the upper extremities, of course, we have implemented many different kind of games which are close to functional activities of daily life. For example, here there's a cooking scenario where the patient has to grasp different meatballs to place them in the saucepan. Before that task, they can also cut the ingredients used for cooking. They can use a plate, fill a glass of wine. Next. Here you see an example of different tasks which we have implemented. The therapist, together with the patient, can choose the right games or tasks, functional tasks, which are most relevant to train different kind of movement directions and capabilities of the upper extremities. Next. We also implemented collaborative training tasks where one patient can play against another patient in the same room or remotely to another room. We even adapted the difficulty levels in that way that a patient who is usually not that good performing in that games can play against a healthy subject, for example, against the grandson or nephew or daughter, in order to further engage the patients. Here you see the newest version of our device. It changed the name to NEXO. It's a collaboration with Professor Hutter, who developed special actuation units. And we can do now very fast games. The mass, the inertial mass and the gravitational mass of the robot is much smaller now. And we can also get a much larger range of movement so that we can do different kind of versatile applications of the device, and are using it now soon for training with patients. Next. So you've seen now different applications of robots used for therapy and training with the goal to improve the functional performance, the biomechanics, the muscular and neurological activity of the human subject. However, there's another big field of applications for robots in rehabilitation, and that's in assistance. You see here, for example, a device from Fluor Intelligence, and that's another device from Maya Swiss, which we developed in my lab, a soft exosuit, which we use now for treatment of different kind of patients with muscular weakness, neurological diseases, dystrophy, orthopedic problems, spinal cord injury, traumatic brain injury, Parkinson's disease, multiple sclerosis, cerebral palsy, and so on. The device is already also commercially available, and the long-term goal will be to also use it for elderly who suffer from muscle weakness, and to use it not only as a therapy device, it can be used for both sides, for therapy training, but also for daily assistance. It's affordable, or let's say cheaper than other lab devices, so that people can buy it for their home use, and that's already done by several patients. Next. Here you see one patient who took part at the Zurich Marathon, more walking than running, but still he could go about 8 kilometers in that race using that device, and usually he can just go several hundred meters without the device. So that device already supported him to get a much longer distance. Next. Yeah, that's the idea, to apply that device for clinical therapy as well as for daily assistance. Next. And we have now developed another device for the upper extremity. Next. What we see with these assistive devices, and now you can click twice, is that there's a challenge with these devices to interface them with the human subject. The control of the device is not that easy. Furthermore, we have a challenge with energy supply and weight. And that leads to a reduced acceptance of these devices for these people with impairments. And that's the reason why we next introduced the Cybathlon already 5 years ago, the first one, where we engage and promote the development of that kind of technologies. We got more than 70 teams into the stadium, and they competed against each other, showcasing the best technologies. Next. For example, in the development of exoskeletons, we also had races using prostheses, brain-computer interfaces, and so on. So thank you for your attention, and I'm ready for questions later in the Q&A round.
Thank you, Professor Reiner, for the interesting talk. Now, please allow me to introduce our next speaker, Professor Le Xie, professor at National Digital Manufacturing Technology Center, Vice Director of Rehabilitation Engineering Institute, Shanghai Jiao Tong University. Professor Xie is Vice Chairman of Digital Medical Institution of Chinese Medical Association. He has presided over 20 national research projects on surgical robot and a rehabilitation robot, virtual reality and virtual surgery. Professor Xie, the floor is yours.
Hello, everyone. Good afternoon. I'm Le Xie from Shanghai Jiao Tong University. My presentation is the virtual reality in rehabilitation. Our label developed the virtual reality training system for robot assistant for upper limb rehabilitation. The neural rehabilitation robot include in general 3 parts. The one is the robot mechanism, and the second is auto control, and third is the software, the virtual reality training software. It was known the human upper limb have the 7 degrees of freedom. The shoulder journal have the 3 degrees of freedom. The flexion and extension, adduction and abduction pronation, and the supination. And the airborne joint have the 2 degrees of freedom, flexion, extension, pronation, supination. And the Risker joint also have the 2 degrees of freedom, flexion and extension, radial and ulnar. According to this 7 degrees of freedom, our label developer for the upper limb, the rehabilitation assisted robot. And for the rehabilitation training software include the 2 areas, the control panel area and the visual training scene display area. The control pane area can input the patient information, monitor training, the parameters, selecting training model. And the virtual training screen display area, the visual human can respond to the patient's action to complete the game task. In order to implement of the 3D modeling to ensure the model realistic and the joint move smoothly, 3D master is used to the model for the reading visual body. Then to input and join the physical model into the visual environment. Then applying the OpenGL displaying table function. And for the display area include the 5 parts: visual human modeling, positive kinematic analysis of upper limb, illumination and the texture mapping, sensor data reading and conversion, stereoscopic display. We can show the whole system. The students test the robot system, and when the students move, the visual body hand is moved in the same time. We do some clinical experiment for this rehabilitation training system.
是练这个动作，深腕的动作。当然，你肘关节要屈伸，因为你不屈伸也不行。学会了是吧？是练这个动。
So after that, we do another generations exskeleton rehabilitation robot for the upper limb, and redesign the robot. Also for the software, we also develop another generations, so training and the evaluation software can visualize of motion control curve. We developed several game for the training. This game is a small ball to climb the wall. To develop the software, the game, the principle is determine the collision position, and then calculation the time required for collision, then collision rebound. And for the sensor devices implement, the first is the texture mapping, and then illuminator material, music and sound effects. Multiple virtual reality scenarios can be created in the same training mode or motion evaluation mode to increase the patient's interest and save the resource related to the creation of the new game model. Also, to use the SEMG information to evaluate rehabilitation effectiveness. do some clinical experiment. Another patient clinical experiment. And for our label develop another system for the interim neural coupling rehabilitation robot. The rotational orthosis for walking with arm swimming system. So this one include the upper limb and the lower limb, and they move in the same time and can get the better clinical effector, rehabilitation effector. For the training on the robot, the first need the data received from the motor encode, then data transmitted to Unity 3D through TCP/IP protocol. Synchronized movement of the patient in the virtual skin. This developed the software developed by our label. And when the patient training, the people in the virtual environment can move, can work. And another one is the hand rehabilitation and assessment system, which include the hardware and the software. For the software, you use the virtual realities technology. We developed several games. For example, the Harvest Orchard, Piano Master, Happy Pandy. This is the start interface of the game, training the patient's hand fractions and extensions. For the Harvest Orchard, the patient controls the little girl to pick the apple by bending the palm of his or her hand. The Piano Master, the effect of the playing the piano is simulated by synchronized the movements of the patient's hand with the one in the virtual scene. And the Happy Panda, the panda eats the flowing bamboo. The patient is required to bend his hands to control the movement of the panda. The scores taken by the patient within the specified time will be added up. The date will be stored and used to observe the patient's rehabilitation condition. Thank you.
Thank you, Professor Xie, for this informative talk. Now let's come to the Q&A session. So we've already received like 6 questions from the audience. So let's start with the first one. So this one is for Professor Yang. In your presentation, you mentioned the 4C principle. What does compliant refer to? Compliant with what?
Compliant that, obviously, particularly for rehabilitation, that you want the robot, when you want to act on something, then you want the robot to be compliant, i.e. to be, conforming to what you want to do. When you want to have assistance and you want the robot actually to support the action you are going to do. So basically with the force and so on. So compliance is very important.
Okay, thank you. Professor Xie, would you mind turning on your camera? So the next question is, I think it's for all our speakers. It's from Claire Ding. How do you think about using the robots to serve the elderly people in the nursing home? Do you think it will be really workable? Who would like to answer first? Maybe Professor Rina?
Yes, happy to answer. I think there's a great demand, a big need to support the treatment of people in elderly homes from a physical point of view, but also organizational and logistic point of view. So the use of robots is sounds attractive, but as indicated in the question, it is a challenge to make the robots really reliable and versatile to bring a real support rather than a burden for the supporting staff in the nursing homes. In our application, the MyoSuit, for example, helps elderly to move more, to spend less time in a wheelchair or chair, but more time in walking, in upright posture. And that's a more general application, not only related to a nursing home, however. And then that's feasible. That's already being done if the people are able to put the devices on. And
okay. Thank you. Then following the question, the topic of Myo, then we have one specific question from our audience. How much does the Myo exoskeleton suit cost per unit compared with the version developed at Harvard? I don't know whether you could provide an answer.
They mean the MyoSuit, I guess, with Myo?
Yeah, the MyoSuit.
Yes, the MyoSuit costs only about $7,000. Plus some extras if required for special software or special maintenance maybe, but it's really affordable. I mean, at least for hospitals, also for some private people who are a bit wealthier, of course, it's price of a half a car, let's say, or of a motor bicycle. So I think it's affordable. It's about 10 to 20 times cheaper than the competitors.
Okay, thank you. Then let's coming back to the previous question about using robots to serve the elderly people in the nursing home. What's your opinion on it? What's your view on it, Professor Yang?
Sorry, can you repeat the question?
Yeah, how do you think about using the robots to serve the elderly in the nursing home? Do you think it will really be feasible?
Yeah, so I think the answer to that question is yes. And the consideration we need to bear in mind, I think exactly as Robert is mentioning, that needs to make it to be cost effective and reliable. And more importantly, I think it needs to be able to be integrated with the daily living very well. So it cannot be, for instance, bulky and also that it needs to be able to cater for the daily activity very well. So there is one class of those robots which will enjoy the first use. It will be those wearable systems. So for instance, for patients with Parkinson's, for instance, that to manage the tremor, to give them the dignity, to be able to integrate with the social life better. So those kind of wearable robots, you will see a lot more. And secondly, that those robots will be able to provide assistance. For instance, many people are using vacuum cleaning robot nowadays already. So those are small robots, they'll be able to roam around the home, but also provide certain function, and those will come. The very big exoskeletons and also those costly rehabilitation robots, these will probably unlikely in the near future will be, in my view, to be used in the home environment. So I think from our research community, also for companies, we must bear all this in mind: cost effectiveness, easy to use, safety, and all these factors.
Okay, thank you. Then the next question is for all the three speakers. It's a general question pertinent to all professors. So what are the biggest challenges in your research areas that you don't see a clear solution yet, either technically, commercially, or ethically? Maybe Professor Xie, could you start first?
Okay. The virtual reality, the technology used in the rehabilitation, it's very useful, but it's also have the challenge. For example, the translation speed may be a little challenge, and another one is the more the patient's information will be input in the system will be also the challenge. I think it's that.
Thank you. And Professor Rina?
Yes, I would say that we still have to do a lot to make the systems more user-friendly. That not only an educated engineer or therapist can control the devices and operate them, but also any patient can use it and even get motivated because it's fun to use. And that includes, for example, the games. Our games we develop, and I include my lab itself to that, are kind of very old-fashioned and very simple. And the young generation are much more, let's say, spoiled by this very good graphics from all these computer games. And I think there's a chance to make our games much more attractive, for example, to get a better user acceptance.
Thank you. Then Professor Yang, could you share us your view on it?
So for us, it's really what we call the new materials, or called the smart materials. It's a very big challenge for us, and also I think if we can crack this problem, this will significantly enhance the usability and also the diverse range of applications we can think about for home or rehabilitation and assistive devices. The reason is very simple. In today's talk, that all speakers mentioned the need of those lighter devices for rehabilitation, and I briefly mentioned about the soft exoskeletons. So in the current generation, that it's very much what we call the hybrid, hard and soft materials combined together. But we are working on those smart materials, smart fibers, not only can provide you with the sensing capabilities, but also be able to provide you with the actuation. So initially, perhaps that mainly for dampening the motion and for certain amount of assistive function, but in future, they will be provided much stronger force, give you the supportive function that can be used for lifting and so on. I think this is really an area very exciting. That a couple of years ago, that we have an editorial on this very topic. Smart materials be able to provide sensing, actuation, and also computation at the same time. So if we can do all this, imagine 20 years or 30 years down the line, those innerwears or those garments we wear, that they can not only provide the sensing capabilities, also all this actuation supportive function we are talking about today. Then this will really make those devices to be wearable, and this is really the exciting area for wearable robotics.
Thank you, Professor Yang, for the insight. And then the next question is for Professor Rina. As the initiator of CyberSlone event, could you share with us how you came up with the idea? And are there some major trends that you have observed over the past editions of CyberSlone?
Yes, the idea came because I saw how terrible the function is of many devices which are even available commercially, like prostheses for the upper extremities. They're so complex sometimes and so difficult to use that they're not accepted, and then they're ending up in a drawer, not on the arm stump of the patient. Wheelchairs cannot climb stairs or just go even over uneven terrain. And if they're able to go over uneven terrain, they do not fit through a door into a house. So we said we have to improve the technology and make it more acceptable finally. That's the first motivation I had. And then I saw that we still have to do a lot to better include people with disabilities. CyberSlone is made less for therapy, but more for promoting the development of devices for assistance. and the assistance is required by people with disabilities. And often they are kind of discriminated or at least ignored because there are barriers in our environment, and even more, there are barriers in the heads of the people, in the brain of the people, in the way how people are treated with disabilities and forgotten often. We want to make a step towards a better inclusion. And to the second part of the question, yes, there have been trends already, because we have now some devices which were extra developed for the Cybathlon, which are now commercially available. All devices which were which were in the lab, where the translation to a product was accelerated, and where the Cybathlon could be used by companies, for example, like Össur or Rewalk or Otto Bock, for example. The Cybathlon could help those companies to advertise their device, which is also nice, because finally we want to make the devices applicable to the patients to improve their life.
Thank you. Then the next question, I think it's very technical for all the speakers. So frailty syndrome is very common among older people. One of the possible symptoms of frailty is decreased hand grip strength. Is there any robotic device available to train the hand muscle strength, which are small and handy? Maybe Professor Yang?
There are, in fact, multiple devices that can do this. So those, soft robotic gloves that can provide the resistance and also supportive functions, and can be used for that purpose. So I think from that perspective, in fact, there are quite a lot of those devices available. But what will be interesting is that in future, whether you'll be able to have a device that will be able to provide assistance as well as training at the same time. So back when I was at Imperial, that we had this project for astronauts. That the idea is that really to have a device that can be used for training and also assistive function at the same time. So you can think about, one device serves its due purpose. But what will be even more interesting is that to have a device to be able to sense that how much assistance is needed, because you don't want to provide, when you have a certain amount of force and you want to have small amount of assistance, but when you're getting more and more frail, that you want to provide more assistance. So this is really that there's a human robot symbiosis that, be able to understand what's going on, to provide assistance when needed, and also appropriate amount of assistance. And this is really that, I think, for assistive devices and assistive robots, where the research committee, are putting a lot of effort into.
Thank you, Professor Yang. Yeah, Professor Reed.
Yeah, I fully agree with what Professor Yang said. I just want to add that it's that the robots are not miracles or providing miracles to the body. We still need the compliance and readiness of the patients to contribute. That means they also have to be active, they have to come, and they have to training. Many trainings can also be done without devices, maybe less efficient, but possible. So we need both good robots with the right amount of assistance, as Professor Yang said, maybe, and good patients who want to learn and who are active.
Yeah, thank you. Professor Xie, do you want to add something to this question?
Okay, I think this one is important because can you hear me?
Yes, we can hear you. Now you are mute again. Can you turn on your mic?
Okay, yeah. And the virtual realities the developed quickly in recent years. We can use the new technology. For example, use the glass, the very light glass. Can use in the eyes. Maybe in this kind, you use this kind of the technology, maybe the patient will get more the interest of for the training.
Mm-hmm. Thank you. Then the next question is, I think it's also partially mentioned by Professor Rina already. So gamification has been mentioned in several presentations. How much do you think will rehabilitation robotics connect with the video gaming industry in the future?
I can say something to this. That's a very good question. And indeed, we in my lab are now forming a new group, a new company finally, which has the goal to connect existing games, which are very popular and which are very well advanced, which have a very high level of realism and interactivity, use exactly these games for the operation of our rehabilitation robots. And with this, we hope to make a breakthrough that the robots are really being accepted and used for a long time to improve body functions.
Okay. And how about Professor Yang? Do you have any comments on that?
Yeah, I think that gamification is a very practical way of integrating this into the rehab environment. In fact, that Professor Rina has been doing a lot in this area, and so does Professor Xie. And I think the next stage is really make a full use of those what we call the augmented reality systems. So to provide what we call the in context, in time assistance combined with those kind of training. So make it even more interesting. So not just sitting there playing a video game per se, but it's a real interaction with the environment. And I can see that those type of things will start to appear more and more in future.
Thank you, Professor Yang. Then Professor Xie, you also showed us some example of games, the small games like the picking the fruits, also playing the piano. So can you also share with us some insights from your research experience?
Yes, and I think the maybe this kind of technology can develop more for the patient, the training at home maybe is better, and also for the children because some children also need the rehabilitation.
Okay, thank you. Then due to time constraint, I think I will ask one last question to our speakers. So elderly people tend to fall due to muscular or skeletal weaknesses, causing severe health consequences. Are there any products or research projects that could offer a solution? Maybe Professor Yang?
Sorry that I missed the first two sentences that
the question was elderly people tend to fall due to muscular and skeletal weaknesses, causing severe health consequences. So are there any products or research?
Yep. So fall detection is very important. So in fact, your question has the three elements there. Number one is that how to prevent fall. And the second one is that to strengthen the musculoskeletal strength. So for which I think those questions being answered in previous questions. And thirdly, that is that in the home environment, that what are the solutions you can provide. So I can answer the first part, and maybe I'll ask ask Robert and also Professor Xie to add in for the third one. So the key question for fall is that to prevent the fall in the first place. So with this, that it's very important that there are many things you can do. One is that to be able to real-time monitor the gait. As we know, when you have unstable gait due to frailty and so on, then what you want to do is that don't let patient or elderly to do things that are too risky. So in fact, at Imperial and so at the IMR at Shanghai Jiao Tong University, we have this little air-worn device, which I didn't have the time to explain or to show today, is be able to pick up gait that in the home environment, normal living environment. And it can detect ground reaction force and also that the body sway, trunk motion, and so on. So when you detect unstable gait, then we provide warning and so on. So what you can do then, think about, for instance, if you have a soft exoskeleton, let's say, then you will provide more support or more restriction to stabilize it. Otherwise, that you will let the patient to more freely and so on. So those type of systems, not complete solutions as yet, and certainly that are available in the lab environment. Maybe Robert, you can add that from your lab's work.
Yes. So it's important that one reason for falls is muscle weakness, anxiousness, too little training of gait, because people are sitting too long, and that's also one way how we can improve prevention. That's by training, and then of course there are many devices, even commercial available, that protect the people if they fall, and other devices are there which avoid falling. So exoskeletal devices can support to avoid falling, for example. And what I've seen just recently is a kind of an airbag system, which is blown up when the patients are already falling, and in this way protecting the bones, the pelvis, the femur from fracture and injury when they bump onto the ground, and that seems to work as well. So there are indeed now more and more methods and technologies which help prevention as well as detection, as well as worst case fractures of falls.
Okay, thank you, Professor Rina. Then Professor Xie, would you like to add something to the question?
And I think the more game will give the patient the more the choice, and will give the get better for the rehabilitation, the training.
Okay. So due to time constraints, we will have to end this dynamic Q&A session. So our great appreciation to Professor Yang, Professor Rina, and Professor Xie for your available time and your deep insights. If you have more questions, please send them to the email address on this slide, and we will forward them to our speakers and give feedback to you. You are also more than welcome to scan the QR code, follow us on social media, and subscribe to our newsletter. So thank you indeed for your active participation, and we look forward to meeting you in our next events. Thank you. Thank you, Professor Yang, Professor Rina, Professor Xie. Bye-bye. Have a nice day.
Thank you so much.
Bye-bye.
Goodbye. Goodbye.